Okay, now I wanted to emphasize the pigments. These pigments here and how we measure their absorbency. I want to mention that chlorophyll type A, it absorbs light to a given percentage, as well as chlorophyll type B. So you realize that carotenoids are also absorbing light. Basophils and phenophytin, all of them are absorbing light, even when you don't see it there. So the green is dominating, but all of them are performing the absorption. But when do they perform the absorption? Each one of them is absorbing light at different wavelengths of light rays, as we know that they have got different electromagnetic spectrum there. Different wavelengths is represented in that beam of light. Now, each of these pigments, they maximize their absorbance in a given wavelength. So you realize that when chlorophyll A is absorbing highly, carotenoids have a poor absorption there. But there will come a situation in absorption that green is absorbing very little and the carotenoid has maximized the absorption there. So it helps a leaf to maximize the absorption, all kinds of wavelengths present in the beam of light present here, or presented on the leaf. So they choose correctly, and that keeps a constant supply of sunlight absorbed in the reactions of the reactions that happened at the thylakoid membrane there. For example here, when we present the action and absorption spectrum, you realize that at some, this is absorbency, right here, absorbency. This is showing the percentage of absorption that has occurred. These are wavelengths as presented by Roy beams. These are the colors present in the electromagnetic spectrum. If you remember your physics teacher, the college must have emphasized that when a beam of light falls on a prism, we expect different colors presented this side here in form of light rays. Or when you simply look at the rainbow, when the atmosphere is highly moisturized at a given end, the sunlight will be showing different colors that are in those particular rays. Another final example that you can take practically is when you put water, when you take water in your mouth and then you blow it in a beam of light. Take water and then you blow it in a beam of light there. Then be very keen and you look at this atomized water molecules. You will appreciate some colors there. And that is indicating the presence of these colors here. So I'm saying that each of those wavelengths is represented by a color. And depending on those colors, we are going to allow absorbance at one time. Absorbance will be shown below and absorbance will be maximized at another. I will give a practical example. When you look at these graphs, I'll show you that this graph here, of course, this curve that is in one is showing the action spectrum. And this one outside is showing absorption spectrum. I will explain why. I want to mention that the absorption spectrum is presented very low down here. Here in 500 wavelengths, we are expecting the green color. We expect green. This is green here. the dominating pigment in the leaf is also green, so we are going to have reflection of those light rays. And that is why the absorbance will be very poor at that level there. But I want to mention where, so here, if we have this as green, expect that this is violet. At this point, we shall have indigo. Blue will be present here. After green, we shall have yellow, orange, and finally red. That is how those pigments are presented. So the smallest wavelength is violet, and the highest wavelength is red. That's how they appear. So we are maximizing absorption. So we are maximizing absorption here where we have violet, because in the leaf we do not have any violet pigment. We are maximizing for that reason here. We don't have any indigo, neither do we have blue. Have maximum absorption. Where we have green, we have yellow. Expect the absorption spectrum to be poor, like that. So the absorption spectrum will be poor there. And then it will again, the absorption spectrum will again increase. We see increasing again after we have reached yellow. So at orange and red, it will be showing the maximum. Light will be very clear in numbers. So what is absorption spectrum and what is action spectrum? So absorption spectrum is that amount of sunlight absorbed by a plant. So you can say the amount of sunlight absorbed by photolight pigments in the chlorophyll molecule at different wavelengths. I want to repeat that one. The amount of light absorbed by a photolight pigment. Now when I say photolight pigment, even if I don't mention chlorophyll, because you understand they are separate now. So amount of light absorbed by photolight pigments in the plant leaf at different wavelengths. That is absorption spectrum. It is not true that all that light that these leaves absorb, they use it. They might absorb of the highest percentage, but they only use a little out of that is absorbed. And now that little used in photosynthesis is what we call the action spectrum now. That is the amount of light used during photosynthesis. Out of that absorbed by the photolight pigments at different wavelengths. So some students can say it is the effective light out of that absorbed by the photolight pigments at different wavelengths. And that one correctly defines what absorption spectrum is and what action spectrum is. So I hope you can correctly give a difference if they ask you to differentiate between the action spectrum and the absorption spectrum. We cannot use all of it because of some other factors that affect that reaction. You might realize that we have high light intensity present. That one absorbed is very high. But some of the other factors affecting the rate of photosynthesis are supplied insufficiently, that we cannot use all the light present to give that relevant reaction. I don't know if that is very clear. That one should be clear. The chemistry teachers have always been teaching you about the Richard-Gere principle, whereby whenever we have reactants in this side, we are going to have equations shifting to another direction to ensure several products are formed. And if we subsequently remove those products, we shall have to facilitate the reaction of these reactants. They give us very many of those products there. I want to relate in biology here. If we have, assume that we have 78% absorbed sunlight, the absorption spectrum, but the carbon dioxide present is as low as 0.04%. It means that you cannot use all of this light together with this very little carbon dioxide. We shall only get a very low percentage, probably 40%, to be involved in this reaction with 0.4 of the carbon dioxide, and now the remaining you will not be utilizing. There will be underutilization of the amount of light present. That's why you see absorption and action spectrum emerge. I want to leave that at that, and then I want to tell you about what happens when this light is absorbed. To which extent is this absorption of this light important during the formation of food in these plants? It occurs in the thylakoid membrane. Occurs in the thylakoid membrane. This reaction of light is then known as photophosphorylation. So they will ask you, what is meant by the term photophosphorylation? This equation can define it. An ATP molecule, together with an inorganic phosphate, will generate an ATP molecule. Sunlight should be present. This is why we need sunlight. In the thylakoid membranes of the chloroplast, I said that in the chloroplast we have several thylakoid membranes that form a grana. In those thylakoid membranes where we have the photolytic pigments, we mentioned several of them. Among them, we talked about the chlorophyll that you know, carotenoids and others. Once they have absorbed light correctly, like we have seen in absorption spectrum, ATP molecule, these are compounds present within the thylakoid membrane. See that? Adenine dinucleotide phosphate. Adenine is a glucose compound from your chemicals of life, but it only has 5 carbon compounds, so it depends on the sugar. We call it adenine. This is an inorganic phosphate. So to say adenine diphosphate, it means that compound, if you consider cyclic form, it has only 2 phosphate groups of it. And then it is forming an adenine together with the phosphate groups. That's why I said adenine diphosphate. We add on an inorganic phosphate. You need that process of addition. It is energy consuming. That's why you provide the energy in form of sunlight to the plant. And that energy provided will now add on, will forcefully add on this other phosphate onto the adenine. Adenine triphosphates. This is the form in which energy in the body is stored. We cannot transfer energy in the body, it will be heat. And this will disturb the homeostatic mechanism of temperature regulation. So we therefore prefer transporting our energy in this form which is not disturbing. That whenever you need it, you will have to break it down with this covalent bond between the phosphate group C. And then to release the bonding energy. You know what we mean? the ATP molecule, it releases energy in form of bond energy. And that energy is what biological processes utilize. That we can break it down it and then we form ADP again and inorganic phosphate. Breaking this bond here, bond energy can be the amount of the energy change that occur. The energy change that occur when one mole of a covalent bond is broken down to constituent elements or product C, not like that. We can even need energy intensively and we break it down in this ADP furthermore, and then we form that ADP can be furthermore broken down to form AMP and inorganic phosphate like that. That means energy is intensively required. I want to go to these details to let you know that plants form ATP for a reason. Plants form ATP because they know they need to use it in another stage where there are active processes which need to be facilitated by energy. And from this ATP, energy will be derived like that. We break these covalent bonds and we give the energy, and then you see other reactions happening there. I want to show you this one here. I want to show you here. They'll ask you, what is meant by photophosphorylation? Photophosphorylation. So the word photo means sunlight. Phosphorylation means the addition of inorganic phosphate on an organic compound. We get an inorganic phosphate and add an inorganic compound. That's what the photophosphorylation. So that's a phosphorylation. But phosphorylation is influenced by light. There should be presence of sunlight there that is absorbed from the electromagnetic spectrum, like I say. So you see that the ATP molecule is formed when ADP and an inorganic phosphate are combined in the presence of sunlight. I want to request that whenever you're writing ATP or ADP, try so much not to abbreviate them like I've done there, because your work will be less doubtable whenever all the ambiguities are removed. I want to mention that there are two types. There are two types of phosphorylation, and the number one is cyclic phosphorylation. And the number two is the non-cyclic phosphorylation. I want us to understand what cyclic phosphorylation is. Cyclic phosphorylation. This is the following the structure of the chloroplast. The chloroplast has got granule. And those granule, we shall choose only one of the thylakoid membrane out of that granule. And we shall call it a photosystem 1. I will repeat for you briefly here the setup of the chloroplast so it will not be confusing. We have thylakoid membranes, several of them, and arranged together to form a granule. Between successful granule, we have an intermembrane or interthylakoid membrane that is connecting to another granule at different energy level. I want to mention that they should be at different energy level. So you realize that if that is there, we must have another, but that is not at the level of this. So this other granule should be at another energy level. So I'll explain why. I want to mention that this granule, we count this granule from 1. So this is 1, this is 2, this is 3, this is 4. Photosystems. These are photosystems. So if I say that we have photosystem 1, I want to mean that it was at the highest energy level of that particular granule. So next time I will happen to mention that this is 1, this is 2, this is 3, this is 4. But now, if I choose to use this photo system and this one, of course this will be photo system 2 compared to this other photo system, because the light exists at high energy level. That existence allows the formation of ATP, like I'm going to show you here. Photosystem 1. During photosystem 1, we are going to have sunlight striking the photosystem 1. When the sunlight strikes photosystem 1, the electrons in the photosystem 1 are going to gain kinetic energy, get excited, and they will be forced to move at high energy level. The electrons will be forced to move at a very high energy level. This movement will be facilitated by electron carriers. These electrons will be accepted by electron acceptors commonly in cyclic photophosphorylation. It's called ferredoxine. This is the electron acceptor. From high energy level, electrons are going to lose energy. When they are coming back to photosystem 1 to stabilize it. And the energy that will be lost when these electrons are coming from high energy level, that energy is used to bind an ADP with an inorganic phosphate to form an ATP. You know very well that when these electrons move to high energy level, they cannot be sustained there. They must come down to high energy level. And here, they will lose energy. The energy they will lose there will allow the combination of ATP and an inorganic phosphate. We put an arrow there to the product ATP molecule like that. Electrons will come back at their original position to stabilize this photosystem 1. This photosystem 1 was unstable ever since it lost some of its electrons to high energy level. As a result of having them hyper-excited due to action of sunlight on the photosystem 1 there. The ATP molecule is formed as a byproduct, and that's what we call photophosphorylation. This one is said to be cyclic because the electrons are taken back from their point of origin, and that is the reason for excitation. So they will ask you what are the products of cyclic photophosphorylation. We only produce ATP molecule, and you will be correct. I will conclude with non-cyclic photophosphorylation here. The non-cyclic photophosphorylation. What is going to happen here is that we are going to have two photosystems arranged at different energy levels. If you remember very well what I communicated previously, so you will know which one is photosystem 1 and which one is photosystem 2 among the photosystems. If you remember correctly, you will know that this is probably a photosystem 2, and this one is photosystem 1, because it is at a higher energy level. Both of them will be excited, will be struck by sunlight at the same time. When sunlight strikes them, like we said, they will both gain a lot of kinetic energy, and their electrons get excited. So we shall see these electrons moving to high energy levels. The electrons are carried by electron carriers, and then they will be accepted. Electrons from photosystem 2 are normally accepted by electron acceptor called plastoquinone. plus to quinine. Electrons from the photosystem 1, they will get to high energy level. That's one will be accepted by theriadoxine. Look at theriadoxine. As these electrons are moving to high energy level, trying to reach the lower energy level because they cannot be sustained in high energy level. From your mechanics, you will appreciate that energy will be lost from them, and they will go to photosystem 1 to stabilize it since it lost its electrons, which has been unstable. When they stabilize it there, it will become stable. However, the energy they have lost when they are coming from the high energy level is used to bind an ADP molecule and an inorganic phosphate to produce an ATP. Now we have this unstable. It has not been stabilized. We shall have another reaction happening here. It's called photolysis. We'll ask you what is photolysis. When sunlight strikes water molecule that is present within those thylakoid membrane, this water molecule will be seen dissociated to produce hydrogen ions. Probably if it's more than one water molecule, we are so much interested to have two hydrogen ions produced together with the hydroxyl ions, several there. These hydrogen ions will move to high energy level in presence of NADP. This is adenine, this is nicotinamide adenine dinucleotide phosphates. Those are organic compounds that exist in the thylakoid membrane. In presence of the electrons on the thylakoid membrane in the ferredoxine here, NADP will bind with the hydrogen ion and it will produce a reduced NADP. And say NADP H2. The remaining water of hydroxyl ions here, they can continue ahead and they react together to produce water molecule plus oxygen gas. You can add 2 electrons this side to balance that reaction there. These electrons produced will come and stabilize the photosystem. And now that is non-cyclic phosphorylation. The products produced include ATP molecule, those are the products of interest, and the NADH2. So I hope the students now will be able to tell when they ask you the oxygen produced during photosynthesis from which molecule is that oxygen. I want to emphasize that oxygen is coming from water. That is the process called photolysis. You will watch that if you want to emphasize. Sorry about that. I want to emphasize that the water molecule produced during photosynthesis is coming from the photolysis of the water molecule. Photosystem 2 is the last electron acceptor. In the cyclic, photosystem 1 is the last electron acceptor. That will be one of the differences among others. When they ask you to give differences between cyclic and non-cyclic photophosphorylation, you realize several. It has photosystem 1, this one has 2 photosystems. It has got only 1 electron acceptor, we have 2 electron acceptor. The product formed here are ATP molecules and the reduced NADP. Products formed there is only ATP. You can generate the others. But I want to say, we are so much interested in these products because are going to be key notes in the darker stage when we are analyzing the other continuing part of how food is formed. Because together we agree that here among the products we have formed there is no glucose. But we are aware that glucose is the main product in photosynthesis. So it means that we have another part to cover to understand how these products of the cyclic photophosphorylation are used in the darker state to generate glucose. You can write some questions here maybe to guide you when you're reading these facts here. And you can write number 1 part A. What is meant by photophosphorylation? What is meant by photophosphorylation? What is meant by photophosphorylation? You write that one there. And then number 2. Explain the significance. Explain the significance. Explain the significance of sunlight energy during the light stage. Explain the significance of sunlight energy during the light stage of photophosphorylation. During the light stage of photophosphorylation. Give it 6 months during the light stage of photophosphorylation. And then finally, part C. You state the differences. State the differences between cyclic and non-cyclic photophosphorylation. Between cyclic and non-cyclic photophosphorylation. Number 2. Number 2 is that describe the structure of the chlorophyll molecule. Describe the structure of the chlorophyll molecule. Describe the structure of the chlorophyll molecule. Part B. Distinguish between action and absorption spectrum. Distinguish between action and absorption spectrum. And finally, part C. Describe how the chroplast